All right, so this is section 11.3, video number 2. We're going to do the next 6 examples in this video, and then we're going to stop the video, and there should probably be a total of 4 videos for this section. So we'll do the next 6 examples. A couple of those will be short, and then we'll come back and do a 3rd and 4th video. All right, so example 7, determine whether the following series converges or diverges. Again, go through all the different processes. Look to see whether you can make this a geometric. It's not geometric. Look to see whether you could possibly do a telescoping. It would have to be, for the most part, some kind of a rational function that we could do. It's not that because you've got a natural log in the denominator. So we're going to look to see whether we can use the integral test. Again, this one is going to be continuous, decreasing, and positive because of the fact that n starts with 2. And that was important in this case. The sum has to start with 2. Can't start with 1 because the natural log of 1 is 0, and then you'd be dividing by 0, and the sum wouldn't make any sense. So let's go ahead and use the integral test. Integral test. Once again, I'm just going to go straight to the limit in this case. So the limit as t goes to infinity of the integral from 1 to t of 1 over x ln of x dx. Okay, so this one is going to be a u substitution. Again, you should be able to recognize that if you let u equal the natural log of x, the derivative of that is 1 over x, which will get rid of the extra x in that denominator there. So let's do that. Let u equal the natural log of x. So du is 1 over x dx. And you can see that that's there. Dx would then be x du. So we'll have the limit as t goes to infinity, integral from 1 to t, 1 over x times u times x du. So those x's are going to go away, which is what we needed. So then we'll have the limit as t goes to infinity, integral from 1 to t of 1 over u du. Of course, the integral, or antiderivative, excuse me, of 1 over u is going to be the natural log of the absolute value of u. This is going to be really interesting. We'll have the natural log of the absolute value of the natural log of x, replacing u. And we'll evaluate that from 1 to t. So then we get the limit as t goes to infinity of the natural log of t minus the natural log of, actually that should, I already made a mistake. Hopefully you guys caught it. That should not be a 1 here because it doesn't start at 1, it starts at 2. Otherwise, once again, it doesn't work. So that was my mistake. Hopefully you guys caught that before going on, but if not, so now we're going to have that from 1 to 2, which means that's the natural log of 2 out there. So natural log of 2 is just some kind of a positive number, don't know exactly what it is. Then if you take the natural log of that, once again, this part over here is finite, so there's no problem there. But substituting infinity in for t gives you the natural log of infinity, which is infinite. Then you'll take the natural log of infinity again, and that's just going to give you an infinite value minus some kind of a finite number. So this one goes off to infinity, which means this is divergent. All right. Determine whether the series converges or diverges. The sum of 1 over n plus 1. Again, go through all of your tests. That is not going to be geometric. It's not telescoping. And I guess I probably should have mentioned we should have been trying the nth term test for divergence on all of these. All of these so far, the limit as n goes to infinity of the nth term have all been going to 0. I just didn't mention that in the previous ones. So that would be inconclusive, which means, once again, let's try the integral test. This one's actually pretty short. So we'll have, the limit as t goes to infinity. This one can start at 1, so we'll have 1 to t of 1 over x plus 1 dx. No u substitutions or anything. This is a constant over a linear function, which means we can just call it, use the natural log as our antiderivative. So we'll have the limit as t goes to infinity, the natural log of the absolute value of x plus 1 from 1 to t, which is the limit as t goes to infinity of the natural log of the absolute value of t plus 1 minus the natural log of 2. Once again, if you plug in an infinite type value into t, you're going to get infinity minus the natural log of 2, which is still infinite. So then this one is also divergent. Okay, so we're moving right along. Number 9, determine whether the following series converges or diverges. All right, so let's look at example 9 here and say, okay, we could potentially do the integral test here, but if you rewrite this sum first, and this is just something you have to look for, this would be the same thing. E to the negative n is the same thing as 1 over e to the n, which is the same thing as the sum from 1 to infinity of 1 over e, the whole thing, raised to the n power. Well, by writing it in that fashion, now this is a geometric. Okay, there's no reason to do the integral test here. It's going to be way easier to use the geometric series test. And because of the fact that 1 over e would be your r value, 1 over e is a number which is definitely less than 1. Therefore, this would be convergent. There was no reason to do the integral test. Does the integral test work? It certainly does. You could have done the integral test and you would have been fine. But in this case, the geometric series test was much, much easier and quicker to use. Okay, will not probably be the case for the next one. Example 10, determine whether the following series converges or diverges. And by the way, on example 9, we could have found the sum. It just didn't ask us to do that. So no reason to go through with that. Determine whether the following series converges or diverges. Again, it's not geometric. No way we can get it there. Can't use any kind of telescoping. I'm not going to go through the process because L'Hopital's rule here, it would take a couple of different L'Hopital's rules to get through this with a little bit of simplification. But ultimately, you get that the limit of that term goes to 0, which is inconclusive. So let's go to the integral test. Again, this is going to be a continuous, decreasing, and positive function. I'm just not going to write it in this particular case, but it is. So we'll have the limit as t goes to infinity, of the integral from 1 to t, natural log of x squared over x dx. Looks like we're going to have to do another u substitution. So u here is going to be the natural log of x. Du would be 1 over x dx, making dx x du. That's good. That'll get rid of that extra x in the denominator. So we should have the limit as t goes to infinity of integral from 1 to t u squared over x times x du. X's will go away. Nicely divide out of there. And we get the limit as t goes to infinity, integral from 1 to t of u squared du. This is a nice easy antiderivative. That will equal the limit as t goes to infinity of 1/3 u cubed from 1 to t. Again, those bounds are really not correct until we replace the u, which we're getting ready to do. So we'll have 1 over the natural log of x, 1 over 3, excuse me, times the natural log of x cubed from 1 to t. So then if we plug in t, we're going to get 1/3 the natural log of t cubed minus 1/3 of the natural log of 1, which is 0. So if we, oops, completely forgot the limit part. That is bad. Very important part, most important part of this whole thing right here, actually. Okay, so the limit as t goes to infinity, once again, if you plug in an infinite value into the natural log, you're going to get an infinite value there. So we're going to get infinity minus 0, which is still infinite, and therefore divergent. Kind of a common theme when we have these natural logs. Not always going to be that way, but in this case, they seem to have been. All right, probably one that is slightly more interesting in this case. We're going to determine whether the series is convergent or divergent. Again, go through your basic ideas. This one is not a geometric. 8 plus n squared cannot be factored in a way that you can use telescoping. The limit as n goes to infinity is 0, so it's inconclusive. What you have to recognize here is that this one looks like, it's not, but it looks like an inverse tangent. It's not exactly in the correct form, at least not yet, not the way I do it. Now, there are formulas that you can use to do this problem, and if you choose to memorize the formula, probably quicker and easier. I've just never been good at memorization, which I'm sure you've heard me say before, so I choose to try to figure out how to do this. So we are going to rewrite this. This is one of the few times I'm actually going to do it this way. I'm going to write this as f of x equals 1 over 8 plus x squared, which is the same thing as if you were to divide the top and the bottom by 8, which you can do. It's the same as multiplying. Basically, we're multiplying the top and bottom by 1/8. Then you're going to get 1/8 on top, 1 plus x squared over 8 in the denominator. Okay, it's getting closer to the correct form that we need it to be in. We're going to keep the 1/8 on top, the 1 in the denominator. I'm going to rewrite the x squared over 8 as x over the square root of 8 squared. Okay, so now we can actually go ahead and set this thing up as an integral. So we'll take the limit as t goes to infinity, integral from 1 to t of 1/8 over 1 plus x over root 8 squared dx. So now when we do this, well, the 1/8 can get pulled out to the front. That's no problem. The x over the square root of 8, I can do a small u substitution on. So we'll say that u is x over the square root of 8, which is the same as 1 over the square root of 8 times x. So du is going to be 1 over the square root of 8 dx. So dx is going to be the square root of 8 du. I know there's a lot of stuff going on in this one. Doing all this so that we can get it into the correct form so we can use an inverse tangent as our antiderivative. So I'm going to pull that 1/8 all the way out to the front. Limit as t goes to infinity, integral from 1 to t, 1 over 1 plus, now I let u be that inside the parentheses, so now it'll be u squared times my new dx, which is root 8 du. Well, root 8 itself is a constant. I can pull that out to the front, so I'll have root 8 over 8. Limit as t goes to infinity, integral from 1 to t, 1 over 1 plus u squared du. Now that is in the correct form for inverse tangent. So we'll get square root of 8 over 8 times the limit as t goes to infinity of the inverse tangent of u. But u was 1 over the square root of 8 times x, or x over root 8. And I'll evaluate that from 1 to t. So let's plug our t in, let's plug our 1 in, see what we get. So we get the square root of 8 over 8 times the limit as t goes to infinity of the inverse tangent of t over root 8 minus the inverse tangent of 1 over root 8. Okay, and the important thing is here is I don't really care what the inverse tangent of 1 over root 8 is. I just know that it's a finite number, which is good to know that. I do, however, care what the inverse tangent of infinity is, because when I plug the infinite values into t, or let t approach infinite values, inverse tangent's going to approach infinity, which we've already talked about. That actually goes to pi halves. So ultimately what I would get here is root 8 over 8 times pi halves minus whatever inverse tangent of 1 over root 8 is. The only thing that matters there, this is a finite number. And because this is a finite number, this one is convergent. Okay, again, it was not necessary to actually find, like, we don't have to know what that sum is approximately. We don't have to know inverse tangent of 1 over square root of 8. But we definitely know that it all ends up being a finite value, which means it is convergent. Okay, again, you can choose to memorize a formula for these inverse tangent ones, which is perfectly fine. I just don't teach them. I don't memorize them myself. But if you want to, they are in your book. You can look them up. All right. Last one that we'll do, and then we'll come back with our third out of 4 videos. Determine whether the following series converges or diverges. This one is really nice because you could look at it, and the first thing you might think, since we're in the integral test, is let's try the integral test. Well, it's not geometric, but the first thing we probably should be looking at is what is the limit as n goes to infinity of n cubed plus 1 over n cubed. Well, that is 1. 1 is not 0. Therefore, this one is divergent by the nth term test for divergence. So that one is finished. All right, in our third video, we are going to come back and we're going to talk about this idea of what is called the p-series. It's one of the easier ones to figure out convergence and divergence from, at least as far as the process is concerned. And then we're going to introduce the idea of estimating the sum using the integral test.